Hi, I'm Shravanti, and I'm going to explain the concept of graph convolution networks, which was first introduced in the paper Semi-Supervised Classification with Graph Convolution Networks with the authors Thomas and Maxwelling. The main goal of this presentation is to understand the message passing technique in graph con nets, provide an intuition behind this concept, and get a better understanding through an example. Now let's try to understand how message passing works in a graph net. Let's consider this example with three nodes, and each node has its own feature representation with values. To represent the edges between the nodes, we use an adjacency matrix A, where the presence of an edge between the node and its neighbor is represented by 1, and the absence by 0. Now, to save the information of the feature representation in the node itself, we introduce self loops such that the node can retain its information. The feature representations can be saved in a matrix H such that each row represents the feature representations of each of the other rows. When the adjacency matrix A and H is multiplied, we can observe that the information of the node 1 and its neighboring node is saved. And the same thing is happening for the other nodes as well. This means that the node retains the information of itself and its neighboring node. Node 2 retains the information of itself and its neighboring node, node 1 and 3. Node 3 retains the information of itself and its neighboring node, node 2. This is message parsing. This ensures that the features of itself and its neighboring nodes are captured. Now, what if the information from one node is much more important than the information on the other node? This can be done by adding a weighted matrix W. In this operation, it can be observed that it results in a weighted average of the weight matrix values with the node values. And these elements can be learned during backpropagation of the graph convolution network. This weight matrix W retains the dimensionality of the resultant vector, where each row has node 1, node 2, and node 3, and two columns representing the two columns in each of the feature mappings. This can be upsampled by introducing more columns, or can be downsampled by reducing the columns in the vector. Now, to get the main idea, this product that we have learned so far is how a graph convolution works. It ensures that the information from the neighboring nodes are stored along with the information in the current node, weighted or unweighted in the graph. Now, this procedure is applied at each layer, similar to kernels in CNN, to propagate information. The layer-wise propagation rule in the paper also applies a normalization matrix using the degree matrix D tilde, which is a sum of all the rows in the adjacency matrix. The adjacency matrix is also added with the identity matrix to ensure self loops. The weights are present at each layer, and after performing this product, a linear activation function is applied, such as sigmoid rel or tanh, and the input vector x is used in the first step. Now that we have understood the core concept, let's implement it to perform semi-supervised classification. Consider a two-layered GCN for semi-supervised node classification. This architecture has C input channels in the input layer and F feature mappings. We first calculate the value of A cap in the pre-processing step and then apply it in the forward mode using this equation, where W0 is the input to hidden weight matrix for a hidden layer with H feature maps, and W1 is the hidden to output weight matrix. And this softmax function is applied row-wise. Now, for semi-supervised multi-class classification, we introduce the cross entropy loss error, L, where YL is a set of node indices that have labels. The neural network weights W0 and W1 are trained using gradient descent. In this work, they perform batch gradient descent, and dropouts are used to ensure stochasticity in this training process. When this architecture is implemented using citation network dataset, each document contains a sparse bag of words used as feature vectors, and the connection between the documents are a list of citation links that are treated as edges. Compared to other architectures, it can be observed that GCN has outperformed in terms of classification accuracy in percentage. This presentation does not cover the derivation aspects, related work, experiment details, or limitations. but rather focuses on understanding how GCNs works and provides an intuition on the message passing technique. Thank you.